Determining a chemical formula from experimental data. We talked about molecular formulas and empirical formulas. The empirical formulas seemed like kind of a useless thing, but this is where they become a little more relevant. The empirical formula can be determined experimentally by taking a compound and breaking it into its elements and finding their masses. From that information, we can get an empirical formula. If we have the percent composition for a compound, we can also calculate the empirical formula. It's important to remember that the empirical formula represents the ratios of atoms or the ratio of moles of atoms. It's not the ratio of masses, okay? So everything has to get to moles before we can do ratios. So we're going to learn how to do this. The hardest part about calculating empirical formulas is remembering what to do next. So here are the steps. I'll go over them quickly and then we'll do a couple of examples. You need to start with the masses of each element that are present in a particular sample. Not the molar masses, but the actual mass of element. Sometimes you're given this, other times you have to figure it out. If you're starting with a percentage, like a percent composition, then you can change that into grams by just say, well, if I had 100 grams of this compound, then the masses of each element would be exactly the same as their percentages. So that's easy. Next, you're going to convert the mass to moles, and that's using the molar mass for each element from the periodic table. This next step I think is a little silly, but you can write a pseudo formula using those numbers of moles of each element as the subscripts. These will not be nice whole numbers. They're probably going to be very messy decimal numbers. But one of our labs where we're going to actually determine an empirical formula asks you to do this step. And so your book talks about it, so there it is. I talked about it. How do we get those messy numbers into whole numbers? We do ratios. And so we're going to find the smallest number of moles, and we're going to divide all of them by the smallest. That will give us ratios. One of those ratios is going to be 1, because it's something divided by itself, and all the other ratios will be 1 or larger. Because this is from experimental data, the numbers are going to be a little bit not perfect. We're not going to end up with beautiful whole numbers because there's uncertainty in all measurements. So we need to have some criteria for deciding whether we can round to a whole number or not. So if it's within 0.1 of a whole number, you can round. If it's different, like if you get 2.25, that's not within 0.1 of a whole number. You can't round it. What do we do if we can't round it? We multiply. Yes?
Okay, so I was doing the homework last night, and I had a number that came out to like 0.7 instead of 0.66 or 0.75. So I think I had to round it. Is that okay?
Okay, so what if you get a fraction that's not quite one of these? Well, 0.7, like you ended up with, I would try multiplying by 3. And probably that'll be good enough. So understanding fractional relations between the decimal form and fractions, like 0.25 is 1/4, right? And 0.5 is 1/2. If you multiply that by 2, you should get a whole number. So you can use this little table or your knowledge of decimal equivalents of fractions, but still take the whole number that you've got and multiply by 2, 3, 4, whatever, and then look at the result. If that's within 0.1, then you round, and that was the correct thing to do. If this part just doesn't make much sense to you, there's also the trial and error method, which in this case works pretty well. If you can't round to a whole number, try multiplying by 2. If that's still not close enough to a whole number, go back to the original number, multiply by 3, then try 4, then try 5. Yes?
Well, we have to memorize these.
You do not have to memorize these now. You can always do the trial and error method. Almost never go past 5, so it doesn't involve many tries. Okay, so let's do a couple of examples, and hopefully this will become more clear. A sample of a compound is decomposed in the laboratory and produces 165 grams of carbon, 27.8 grams of hydrogen, and 220.2 grams of oxygen. Calculate the empirical formula of the compound. We can't just take the ratio of the masses. I mean, that would help us to, establish law of definite composition or something like that, but it's not going to give us a formula. We need to convert the grams to moles for each element separately, and then look at mole ratios. So I'm going to take this 165 grams, and I need to put a C there. That's grams of carbon. I'm going to convert this to moles. So I want moles of carbon on top and grams of carbon on the bottom. I look at the periodic table, and I see that 1 mole of carbon is 12.0108 grams. And my units work out, and so that's going to be good. So I do the math. 165 divided by 12.0108. Now, the thing about significant figures in problems like this, in your final answer, the subscripts are going to be whole numbers. So we don't really need to keep track of sig figs, but what we want to do is avoid rounding too much. If you want to use the whole number that your calculator is giving you, that is absolutely fine. More digits is better here. Sometimes students will round things off, and because they're rounding too much, they end up with the wrong subscript. So my calculator here is giving me 13.7. Now that would be the last sig fig following the rules, because this is 165, 3 significant figures. I would definitely not want to round this to 14. That would be a bad idea. The 13.7, I'm going to go ahead and write down a couple more. That's definitely safer. So I'm going to write down 2 more at least. I'm going to go for 3 because I don't like rounding. So that many moles of carbon. And then I look at the mass of hydrogen, 27.8 grams of hydrogen. And it's a similar calculation with moles of hydrogen and the molar mass. Oh, blanky. 795. And so the grams cancel out. 27.8 divided by 1.00795. So this is giving me 27. That should have 3 sig figs again. 27.5. And then I'm going to just write down 3 more for good measure. So that's moles of hydrogen. 220.2 grams of oxygen. One mole of oxygen, 15.9994 grams of oxygen. And I'm going to get 13.76. That's my 4 sig figs that I have to keep. And then I'm going to throw in a couple extras. Moles of oxygen. So the pseudo formula would be using these numbers. Are any of these numbers, well, never mind. We're not at that point yet. Okay, so what do they mean by the pseudo formula? Carbon would have a subscript of 13.7. Hydrogen would be 27.6, and oxygen would be 13.76. Does that look like a proper chemical formula? No. A chemical formula, an empirical formula, is going to give us the lowest ratio But most importantly, the subscripts have to be whole numbers. Because this can't possibly describe what's in one molecule, right? You can't have 13.7 atoms of carbon. You can't have a family with 2.2 children. That might be the average, but you can't have 0.2 children, can you? Has to be whole numbers. So the way we change these into whole numbers is we go with the ratio. So we look at these different molar amounts, and we find the smallest one. It's this one. So I'm going to divide all of them by the smallest. So I'm going to divide this one by 13.7376. That one's going to come out to be exactly 1. And I'm going to divide this one by 13.736. So that's 6. So 27.5807 divided by 13.736 equals 2.0079.
Technically, isn't it 13.7376?
Yes, because I copied it wrong. Thank you. Yeah, I lost a 7 in there. So this comes out slightly different, but not much. 2.00767. Well, 768. Is that close enough to a whole number that I can round it?
Yeah.
Yes, it is. Let's go check this other one. So dividing here by 13.7376. I'll do it correctly this time. This comes out to be 1.0018. Can that be rounded to a whole number? Yep. So we're going to call this 1, and we're going to call this one 2, and one of them is always going to be 1. These are the subscripts. It's 1 carbon to 2 hydrogens to 1 oxygen. And so we write that as CH2O. The ratios in this formula are the same as the ratios in this formula, but this is expressing them as whole numbers. And this can describe what's actually in a molecule: 1 carbon, 2 hydrogens, and 1 oxygen. Any questions?
It's when those aren't able to round like that. They're not within 0.1.
Yeah, if this was 2.5, then we have to do something else.
Can you do an example of that?
Yeah, yeah, I can. How about this one?
No, not that one.
No, that was not a setup question, actually, but this is exactly what you want. So here we're going to do another example of calculating an empirical formula. Here we're given percent composition instead of mass. So 75.69% carbon. What's the mass? Well, it depends on the sample size. If the sample's 100 grams, then the mass is 75.69 grams. And that's easy. There are several kinds of problems in chemistry where you can choose the amount, and you can choose to make it easy or you can choose to make it difficult. But a percent composition does not depend on the amount of substance. It's one of those intensive properties. If you have a truckload or if you have a handful of ibuprofen, the percent composition is the same. And the empirical formula is going to be the same. So it's okay to say, I'm going to assume a 100-gram sample. That's just making things easier. So we take the percentage. First we have to select a pen tool. You'd think I'd remember that by now. 75.69 grams of carbon. Instead of writing percent, I just write grams. And then we use the molar mass. We don't have to remember, are we multiplying or dividing? We just look at the units and they tell us what to do. 75.69 divided by 12.0108. This should have 4 sig figs, so I'm going to write at least 4. So there's 4, and I'm going to throw in a couple more. That's moles of carbon. How many grams of hydrogen am I going to use? 8.80 grams of hydrogen. So 1 mole of hydrogen, 1.00795 grams. And this is giving me 8.73. There's my minimum sig figs, and I'm going to throw in a couple extras. For oxygen, it's the percentage expressed as grams. Oxygen, 1 mole of oxygen weighs 15.9994 grams. So 15.51 divided by 15.9994, 0.969411. Any questions? Converting grams to mole or moles to grams is something that chemists do just like all the time. And so it's really, really important to have that one down cold. I could write a pseudo formula. I don't see the point, so I'm not going to. I need to get these into whole numbers. I can't just round them off. If I rounded them off, I'd have C6H8O. And we'll find that that's not going to be correct. I need to take the smallest. So the oxygen is the smallest, and I need to divide all of them by the smallest. So 0.969411. And these problems are more tedious than they are difficult. You kind of end up doing the same thing over and over again. So this comes out to be 9.006. And this comes out, let's see, 0.969411. This equals 6.5007. Can I round those numbers to whole numbers?
Yeah.
All but the first one. All but the first one. 6.5. I can't round that. So I've got that number in my calculator. I'm going to multiply by 2. Times 2. And that gives me 13.001. Can I round that? Yeah, so that would be 13. Now, we are looking at the ratio of carbon to hydrogen to oxygen. If I multiply the carbon by 2, I have to multiply the others by 2 in order to keep the ratio the same. Does that make sense? So even though this is a nice number that could be rounded, I still need to multiply by 2. So I multiply that one by 2, and I'm going to get 18.012. Close enough to round to 18. That's 18. And then this guy, oh, I lost him, times 2, that's going to be 2. So those are my subscripts then. So this is carbon 13, hydrogen 18, oxygen 2.
And then if they all have a common denominator, you divide it, right?
If they had a common denominator, you'd divide and simplify, but they won't. Unless you did something funny, like if you multiplied all of them by 4, and it didn't need to be that high, then you'd see something like that. But you usually won't see anything like that. Any questions? Yes?
When you divided 6.3018 over 0.964, how did you know to stop at the 7 when you got 6.5007?
Okay. I had 4 significant figures over here, and so I want to keep at least 4. These are zeros. And the 5 is really the important thing over here when we get to the ratio. But I wanted to keep at least my minimum number of sig figs. Keeping more is always better in these sorts of problems, because we come down to a number that we can round to a whole number, and then the sig figs don't matter anymore.
What if you used all of them that you got in your calculator?
If you used all of them that you got on your calculator, you'd come up with the same answer that I did.
Okay.
Yeah. What happens is sometimes students will get a little crazy and they'll just keep one sig fig here. They'll keep 6, and then they'll round that up to 9, and that is really, really not okay. And like down here, it's possible that if you just kept the first 2, that it might have changed something. And so you want to avoid rounding errors. Yeah.
Do we just keep it in the order that they have it?
Good question. We talked about a little bit about the order that nonmetals are listed in molecular compounds. And you have been given that guideline. We're not going to make a big deal out of it in Chem 1A. I think for these problems where you're going to see some combinations of elements that we're not going to see in nomenclature, I think the safest thing is just to keep them in the same order that they were presented in the problem. So you really don't have to think about it. They gave you carbon first and then hydrogen, oxygen. Just keep the same order. Any other questions?
Yeah, when you're given a question like this, the mass percent, you can just put grams, make that.
Yeah, you can do. It seems a little like flippant, doesn't it? It's like, oh, well, what's the reasoning behind that? Well, let's say we had a 100-gram sample. So if we had 100 grams of the ibuprofen and we multiplied, that means there's 75.69 grams of carbon per 100 grams of ibuprofen, right? And so when we multiply, not only do the grams of ibuprofen cancel out, the hundreds cancel out. And so in that sample of 100 grams, we do have 75.69 grams of carbon. So by choosing a 100-gram sample, you can do that. You could use a different sample size, but then you'd have to do calculations to find the mass of each element. Okay? Any other questions? So that's the empirical formula. It gives us the lowest ratio. But the molecular formula is really the most useful formula because it tells us how many atoms of each element are actually in one molecule. The molecular formula is always a whole number multiple of the empirical formula. If the molecular formula is the same as the empirical formula, it's just multiplied by 1. But it could be 2 or 3 or 17. Okay? So to find the molecular formula, we need the molar mass. The molar mass of the compound is something that we can obtain using mass spectrometry. In Chem 1A, we don't do mass spec. So you're going to encounter problems like this in mastering chemistry and on exams and things. The molar mass has to be given to you because you have no other way of finding it out. So we have to tell you what the molar mass is. Sometimes we'll give you the empirical formula to make a really easy problem. Other times we'll make you calculate the empirical formula like we did in the last 2 examples. So the molecular formula is equal to some number n times the empirical formula. So we find n by taking the molar mass of the real formula and dividing it by the mass of the empirical formula. So let's do an example of that. Compound has the empirical formula CH and a molar mass of 78.11 grams per mole. What is the molecular formula? We need to find out how much 1 mole of CH would weigh and divide it into the 78, and to see how many times bigger the molecular formula is. So the molar mass for CH, there's 1 carbon and 1 hydrogen, so it's 12.0108 plus 1.00795. So 13.01875 grams per mole. Now, this 13 is not the same as 78. So this is not the molecular formula. We're going to take the molar mass that we were given, 78.11 grams per mole, and what we want to know is how many times bigger is it than our little 13.01875. So when I divide that, my calculator shows me that's 5.9998. Unless you did something wrong, these will always be very close to whole numbers and you can round them. If it came out to 5.5, I would have to go back and check that I talked to my calculator correctly, that I found the empirical mass correctly, because I must have screwed something up.
What if it was like 5.1? Would it just be considered 5?
If it was 5.1, yeah, you could round it to 5, and that would be a poorly set up problem. So this is 6. Question?
But you said we're okay though with keeping all of our masses to 4 sequence?
Yes, you can do that. So the thing with significant figures is that when we really understand significant figures, we can recognize when we can kind of skimp on those and when it's really important to keep them all and keep track of everything. This is a place where more is better. And so just writing down a handful of them is probably easier than necessarily trying to keep track of exactly how many, because this number is going to be rounded to a whole number anyway. So the 6 means that our molecular formula is 6 times bigger than CH. So we could picture it like this. We got CH times 6. We don't write it like that. We go ahead and distribute the 6 to all the subscripts. So this is the formula. Because in CH, each of these subscripts is an understood 1. 1 times 6 is 6, and 1 times 6 is 6. Any questions?
Wouldn't another proper way to write it be 6CH?
You mean like this?
Yeah.
What that says to me is 6 moles or 6 molecules of CH. So for your own little notes and showing your own work, that's fine, but this would not be an acceptable answer. I know what you mean, but it doesn't really communicate it very well. Any other questions? Combustion analysis is a common technique for identifying empirical formulas. This is especially used for organic compounds that contain only carbon, hydrogen, and oxygen. So we know the mass of the substance, and then we burn it. And all the carbon from the original compound forms CO2, and we can catch that and weigh it. All the hydrogen from the original compound becomes water, and we can trap that and weigh it. We can't trap the oxygen, but law of conservation of mass says that the mass of carbon, oxygen, and hydrogen produced has to equal the mass of the sample that we started with. And so we can find it by difference. This is a picture of, or an illustration of, a combustion analysis device, I guess you could call it. So we have this little combustion chamber, a furnace. You put your sample in there, oxygen is fed in there, and this is ignited, and it burns. As it burns, it produces carbon dioxide and water. And there's a stream of air with oxygen flowing this way, and so they're going to be forced through these U-shaped tubes. And in this first tube is a substance that absorbs water. So this will trap all the water that's coming through. The carbon dioxide will keep going. The carbon dioxide then comes over here, goes through this tube, which has a different substance in it that absorbs the CO2 and traps it. And then anything else just goes out the other end. So we weigh this tube before the combustion, and we weigh it after. And the difference is the mass of water that was released during combustion. Same idea here. Weigh it before and after. The difference is the mass of carbon dioxide. Any questions? So here's the sort of data that we would get. I'm not going to make you draw a combustion analysis picture or anything, but if you were given a problem like this, you should be able to solve it. Upon combustion, a compound containing only carbon and hydrogen produced 1.60 grams of CO2 and 0.819 grams of H2O. Find the empirical formula of the compound. We need mass of carbon and mass of hydrogen, and then we can do those steps that we learned to get the empirical formula. But they didn't give us mass of carbon. They gave us mass of CO2. So we've got this mass of CO2. What can we do with that? And we want grams of carbon. We learned how to do this earlier. There's a relationship in here between moles and grams, right? We can find the number of moles of CO2. I actually didn't give myself enough space. If we know the mass of CO2, we could figure out the moles of it, right? The formula gives us that relationship that there's one carbon for every one CO2 molecule, which means there's 1 mole of carbon present in 1 mole of CO2. It's the subscript on carbon in the formula that tells me that. Does that make sense? So for moles of CO2, I can go to moles of carbon. And then the molar mass of carbon on the periodic table will get me grams. I knew something was not quite right. So let's think ahead. What did we do with mass of carbon to find the empirical formula before? We started with the mass of carbon, and the next step was converting it to what? Converting it to moles. So this is what we're going to convert it to. So maybe there's really no point in going all the way to grams. If we just stop here, we're going to have moles, and that'll save us some time, right? So we actually don't need to go that far. Because the other steps we did mass to moles, and then we did ratios. So let's just stop at moles. So 1.60 grams of CO2, and we're going to have moles of CO2 per gram of CO2, and then we're going to have moles of carbon, 2 moles of CO2. And all the units are canceling out. This moles of carbon to moles of CO2 comes from the chemical formula. There's 1 carbon in 1 molecule of CO2. How do we get the number for this first term? We need the molar mass of the compound. So I'm going to write that out down here, 12.0108. 1 carbon plus 2 oxygens. .0096 grams per mole. So that's the number I want to stick in here. So 1 mole is 44.0096 0.0096 grams. 1.6 divided by 44.0096 times 1 divided by 1. 0.036. I want to keep at least 3 sig figs. I'm just going to throw caution to the wind and keep 1 extra.